In this video, we're going to talk about Experiment 8, which focuses on gas laws and the molecular mass of a gas. Because we're going to be doing this for two labs, we're going to be doing gas laws in Experiment 8 and then again in Experiment 9. I start Experiment 8 by talking a little bit about the practical applications of gases and gas laws. So one thing that we all know about, and that one thing that we rely on for safety every day, are airbags in cars. And many of you guys know how airbags work. I'll show a quick video as a demonstration. But basically the way that an airbag works is it inflates a bag of air, a bag of gas, actually. And then the person who is rapidly decelerating as the car is coming to a stop because it got into an accident, instead of going forward and slamming into the steering wheel, the airbag that's inflated gradually slows them down over a period of time. So you could see that these people, instead of just going forward and slamming into the steering wheel, they get slowed down slower and more efficiently, and that does less damage to the body. So the way that airbags work is through a controlled explosion. So this is all based on chemistry. And it actually goes even beyond explosion. This is a controlled detonation. So the compound that makes this whole thing work is sodium azide, which is NaN3. And when sodium azide decomposes, it produces sodium, solid, and nitrogen gas. The nitrogen gas is what inflates the airbag. So in addition, you can have a second reaction where the sodium reacts with potassium nitrate. So they add a little bit of potassium nitrate to the airbag mix. And when these two things react, it makes an additional mole of nitrogen gas. So what the engineers are doing is they're taking advantage of this reaction to produce nitrogen gas to inflate the bag, and they're doing it so that when the bag inflates, they have exactly the right volume to prevent the person from hitting that steering wheel. So they're using the ideal gas law to do these calculations. They have to calculate based on the number of moles of the reagents, how many moles of gas they're going to have, and what volume that's going to occupy, and what size the airbag is going to be. So this is all done from the ideal gas law. It's also a demonstration of Avogadro's law, because we're using the number of moles of a starting reactant to figure out the number of moles of a gas and the subsequent volume of a gas that we're going to evolve at the end of the reaction. So there are many applications of gas laws, and they can be useful in predicting the behavior of not only an explosion, but of many other things. So what we're going to look at in the next few slides are some of the behaviors, Boyle's law, Charles' law, Avogadro's law, Amonton's law. We're going to look at those different behaviors of gases and those relationships, and then compare that with the ideal gas law, which combines all of them into one nice equation. So the ones that you've heard about in class are Boyle's law, for example, which says that the volume of a fixed quantity of gas is inversely proportional to the pressure at a fixed temperature. So what we see is as we increase pressure, meaning as we push down on a balloon, for example, so if we start to pump air into a chamber that has a balloon in it, that air is going to start to push on the balloon, and it's going to shrink the volume of that balloon. So we see this inverse relationship between pressure and volume. As pressure goes up, the volume will go down, because we have this competing pressure between the gas that's inside the balloon and the gas that's outside the balloon. If any one pressure changes, then that balance, that equilibrium between those two pressures is going to change. So this is a little practice question. We're not actually going to do it, but it just demonstrates what we're looking at here. So, the pressure of a gas inside of a syringe is 14.7 psi. If the volume is reduced to 3 mils, it reduced from 3 mils to 1 mil, what will the pressure of the gas be? Well, if we're reducing the volume, meaning we're squishing that gas down into a smaller space, we're going to expect that pressure is going to go up. So because now those gas molecules are moving around in a much smaller space, so they're going to push more hard, they're going to push with more force on the surfaces of their container. So you can do the calculation if you'd like, but that just gives you a qualitative sense of what's going to happen. We're actually going to be looking at Boyle's law in a demonstration form in just a little bit. So another gas law that we're not actually going to look at today is the relationship between volume and temperature. So what we see is that if a volume of fixed gas the volume of a fixed quantity of gas is directly proportional to the temperature of the gas at a fixed pressure. So if you kind of hold the pressure constant, And let's think about a balloon that has a gas inside of it. So if you start to increase the temperature of that gas in the balloon, what's going to happen is the molecules that are moving around inside the balloon are going to start to speed up. And if they start to speed up, they're going to start to hit against the wall a little harder. Now, if they're hitting against the wall a little harder and the molecules from the outside, the external pressure stays the same, meaning that's just pushing down with a constant pressure, that pushing force is going to allow the balloon to expand. So the balloon is going to grow in size. So again, you can do this practice question, but one thing that I want to point out though, when we start to use temperature in these ideal gas laws, we have to use temperature on we have to convert temperature to Kelvin. We have to have the temperature on an absolute scale. That's because we can't do calculations with negative values of temperature in the Celsius scale. So the reason why we use Kelvin is because there is no negative. It goes down to 0 and that's it. That's absolute 0. So the reason why I have this practice question is to demonstrate that you can use any volume you'd like, but you have to convert the temperature to Kelvin to use it. So we're not going to look at an example of Charles' law, but this gives you a sense of, again, how these relationships exist with the ideal gas law. Now, the other one that we're going to look at today is we're going to do a virtual demonstration, and we're going to give you the data and basically tell you what happens, is Amonton's law, which is the relationship between pressure and temperature. So in this case, what we're doing is we're fixing the volume. So we're controlling the volume, we're keeping the volume the same, and now we're changing temperature. So as we change temperature again of our sample, let's say that our sample is inside of a fixed container of like a plastic box, for example, and the volume of that box is not going to change. As you raise the temperature, the molecules inside of there are going to speed up, and they're going to start hitting off of the walls of that plastic box harder. And when they hit harder, that's going to lead to an overall larger force on those walls, and that is going to lead to an increase in pressure. So we see a direct relationship between temperature and pressure, such that as temperature goes up, pressure also goes up. So the ideal gas law combines the relationship observed for Boyle's, Charles, and Amonton's law into a single equation. And this, you know from lecture, is PV equals nRT. So we're going to ask the question, how can we use these gas laws to do something useful? And in this case, what we're going to be doing is we're going to be deriving the molecular weight of a gas. And we're going to be determining that experimentally. So what I'm going to show you now is how can we go from this equation to this equation where we can solve for the molecular weight of an unknown. So we have PV equals nRT, and then we have to know what molecular weight is if we want to solve for it. So the molecular weight of a compound is going to be the mass divided by the number of moles. So normally, if you wanted to calculate a molecular weight, you'd figure out how many moles you had, you'd figure out how much those moles weigh, you take the ratio, and then you get your grams per mole of your molecular weight. So because we have an n over here, if we reorganize this equation where we basically put n on the left and we put molecular weight on the right, so we get mass over molecular weight is equal to n, we can then plug that in for the n and get an equation that looks like this. PV equals mRT over the molecular weight. And then if we reorganize, basically we move the molecular weight up and move the pressure and the volume down, we get that the molecular weight is equal to mRT over PV. So now we have an equation where we can get the molecular weight if we know the mass of a sample, its temperature, its pressure, and its volume. And this sample must be a gas. So if we know the mass of the gas, the temperature of the gas, the pressure of the gas, and the volume of the gas, we can get the molecular weight. Okay, so this lab is broken up into two parts. So the first part is a demonstration. So we would literally, you're basically not missing out on this demonstration at all, because we would literally do this as a demonstration in class, so you'd watch us do this in front of you. So we have a video of the Boyle's law demonstration. I'm going to show you that in a second. What we're going to do with the Boyle's law demonstration is we're going to observe the pressure of a gas as the volume of the gas is changed in the cylinder. So we're going to see what happens. Now, there's one thing that we have to do in addition to just observing the pressure in the gas. We have to correct for the amount of gas that's in the tube. I'm going to show you how to do that after the demonstration. So we're going to do the demonstration first, then I'm going to show you the calculation for how we get the correction factor for the amount of gas that's in the tube. Okay, and then here's what you have to do. So we're going to give you the data in the data sheet. We're going to give you the pressure, and we're going to give you the volume data. And then you're going to have to make two plots using the graph paper that's in your book. You're going to have to make a plot of the pressure versus volume, and then you're going to have to make a plot of the pressure versus 1 over volume. I'm going to show you in the next slide why we're making these two graphs. But this is what you're going to do with the data that we get from the demonstration. Okay, and then the other demonstration we're going to do is the Amonton's law demonstration. So we're going to observe the change in pressure of a fixed volume of gas at 3 temperatures: room temperature, boiling water, and ice water. And then we're going to make a plot using the experimental data and the data provided on page 117. So I will show you guys that at the end of this video, where the data is going to be. Okay, and then we're going to fit the data and extrapolate the temperature at 0 psi. So we're going to take a look at these graphs now so that you can understand what you have to graph and why. Okay, so for the Boyle's law demonstration, here's some hints with the graphing. So the first thing we have to do is we have to look at what makes a good graph. So one of the graphs that you're going to make is a pressure versus volume graph. So you're going to have a bunch of data points for pressure, and you're going to have a bunch of data points that correspond to a given volume. So we're going to change the volume. That's going to be our independent variable. We're going to basically push in on a syringe and measure how much we push in and change the volume. And then the pressure, we're going to measure using a pressure gauge. So you'll see that in the demonstration. So this graph on the left is what we would call a good graph. And then this graph on the right is what we would call a bad graph. Okay? So let's look at what makes a graph good versus a graph that's bad. Now, the reason why we're going over this is so that when you make your graphs, you know what qualities of the graph, what things you have to do to make sure that you get full credit for your graph. So if you notice, let's just start with some of the basics. The first thing that probably sticks out to you is that this graph, the trace or the data points fill up the entire graph paper, or are at least pretty close to it. You know, it doesn't have to be perfect, but it should be pretty close to filling up the entire graph paper. It doesn't make much sense to have your graph just be in the lower third or the lower quarter of the graph paper. So what you're going to want to do is you're going to want to take your book and turn it so that it's kind of like in a landscape, meaning, or it could be vertical. So you're going to want to decide, do I want to graph this in the vertical or in portrait or in landscape? And then you're going to kind of look at your numbers and make sure that you get as much of those numbers on that graph as possible. So we want to make sure that our data fits and is plotted over a large portion of the graph paper. So the other thing that you notice is, and this has to do with the labels. So you'll notice both graphs are actually labeled pretty nicely. They have, labels every, they're periodic labels at given values. So that's a good thing to have on the graph. Another thing that you'll notice is that this graph has all of it, the axis is properly labeled for both. It has a pressure with a unit like psi, and it has a volume with a unit like milliliters. This graph is missing that volume label and unit, and then this axis is missing the unit psi. So you're going to want to have both labels and units for each axis. And then also you'll notice that this graph has a title, which is something that you're going to want. So there are going to be two graphs. You're going to have one graph that is pressure versus volume, and then one graph that is pressure versus 1 over volume. Now you notice that the pressure versus volume, Boyle's law is an indirect relationship. That means that as one thing increases, the other decreases. So as we decrease the volume, or as we lower the volume, the pressure is going to increase. So you see that this trend that we see in the pressure versus volume is an inverse relationship. So we can correct for that, or we can create a straight line by plotting pressure versus 1 over volume. This will give you a straight line because now we're plotting this as an inverse relationship. We're saying that the pressure is related to the volume by 1 over. So you're going to get a nice straight line from your data points when you plot it this way. So on half of the graph paper, and I'm going to show you the graph paper at the end of this, so you'll see what you're going to do. The pressure versus volume, you'll have a graph that has the pressure versus volume, which will have the inverse curve, and then you'll have the pressure versus 1 over volume, which will be a line. Okay, now for the Amonton's law demonstration, what we're going to basically do is we're basically going to take the pressure at a bunch of different temperatures. So we're not actually going to do this demonstration because it's a very simple thing. We're just going to take a sample of gas and put it at different temperatures. Then we're going to measure the pressure. But when we do that, we're going to get some data points and we're going to plot them. So how do you plot this the best way? So what we're going to do is we're going to have temperature on the bottom. It's going to be in degrees Celsius. And we're going to have pressure on the left, and you can use pressure in PSI. Now, for this graph, what we want to do is we want to plot the data points. And again, just like we did for pressure versus volume and pressure versus 1 over volume, we're going to put our data points on, and then we're going to use a ruler to make a best fit straight line through the data points. So you can use a ruler also for the pressure versus 1 over volume graph. Now, for the pressure versus volume, you may have to get a little creative because we don't have the French curves. So you'll just have to do your best making the line through the points. Don't worry, we won't be grading like if if it doesn't look right. Just try to make a good best fit line through those points. Now, with the pressure versus 1 over volume and the Amonton's law data, you should be able to use a ruler because there'll be lines. So now with the Amonton's law, we're going to do something extra. So not only are we going to put a best fit straight line, you have to draw your graph so that the data continues all the way out till where it touches the x-axis. Because what we're looking for, so you're going to extend your line all the way down until where it hits the x-axis where the 0 is here. And you're going to read off the temperature. Now this temperature is going to be a very specific, or close to a very specific number. It may not be exactly the number, but you can see here that this is about negative 273.15. It's not going to be perfectly negative 273.15. It's going to be something a little different because the data is not perfect, but it's going to be something close to that. So this graph is going to demonstrate that as we decrease the temperature to absolute 0, that's going to be the point where we get 0 pressure. So as we decrease the pressure to absolute 0, which is negative 273.15 or 0 Kelvin, at that point we should get 0 pressure. So that's what we're showing with this intercept. So now let's take a look at these two demonstrations. I'm going to show you the Boyle's law demonstration first, and then we'll talk about how we would use the Boyle's law setup to do the Amonton's law demonstration. So this is the setup that we have at Fordham for doing the Boyle's law demonstration. What we basically have is a syringe with a plunger where we can control the volume, and then we have a tube that connects to a pressure gauge on the other side. So there are two parts of the volume. There's the volume that's inside of the syringe and then the volume that's inside the tube and gauge. The volume in the syringe we can measure from the hash marks on the scale behind it. And then I'm going to show you at the end of this video how we correct for the volume that's inside of the tube. So what you're going to see in this video is we're going to basically change the volume and then measure the pressure. So as we push down on this plunger, you're going to see that the pressure is going to go up. And it goes up pretty much, nice and uniformly. So as volume decreases, as we shrink that volume, the pressure is going to go up. And then as we return it back to where it was, as we increase the volume, the pressure goes down. So this shows that nice inverse relationship. So in a couple of seconds, I zoom in on the syringe and the pressure gauge. So you can see as we raise that volume up, the pressure gauge is going to show an increase in volume. Okay, so now with Amonton's law, we're going to use this same basic setup. So I'm not actually going to show you Amonton's law, but I'm just going to explain what we do. We take the same basic setup. We have a pressure gauge, we have a tube, and instead of hooking that tube up to a syringe, we hook the tube up to this copper metal sphere. It's basically just a spherical container for a gas. And then we take that sphere and we measure the pressure using the gauge at different temperatures. So we start with just room temperature. So you can actually see that here. The room temperature value would be around 14.7 psi. That would be where it would start. just like we started in this experiment. So you'd have your solid sphere with that pressure. Now, the reason why we use a solid sphere is because with Amonton's law, we have to change the temperature but keep the volume constant. So the fact that the sphere is solid means that we can have that constant volume. So regardless of how we change the temperature, the volume of that metal is not going to change. So then what we do is we take that metal sphere and we put it into boiling water, raising the temperature of the gas. And when we put it into boiling water, we're going to see this needle rise and the pressure is going to go up. And you can rationalize that from the kinetic energy of the molecules. When you put it into the boiling water, heat is transferred from the molecules to the gas. The gas molecules start to move around faster and hit off of the walls of the sphere harder. The harder the hits are on the sphere, that leads to an increase in the pressure. The pressure is basically an integration of all of those collisions and the force that it imparts on that surface. So we see an increase in pressure with an increase in temperature. When we take it out and we bring it back to room temperature, the pressure falls back down to where it was to start. Then what we do is we take that sphere and we put it into ice-cold water. And in the ice-cold water, we actually take heat away from the gas and bring it into the ice-cold water. So we lower the temperature of the gas down to 0 degrees Celsius. And what we notice is that the pressure will fall as we do that. As we take the energy away from the molecules slow down. They don't hit on the surfaces hard. The pressure is going to go down. So with Amonton's law, we're going to provide you with the data, basically with the pressure values at the 3 different temperatures. And then we're also going to give you 2 extra values at much lower temperature than we could actually measure in our lab. And from those 5 values, you're going to plot out the Amonton's law graph. So one thing that we have to correct for is the volume of the gas inside the tubing. So as you change the volume in the syringe, we can measure that directly, meaning we can see, reading off the numbers, where we are in terms of volume. The problem, though, is we don't know what the volume is of the air inside this syringe. So there's actually a very simple procedure we can do that allows us to get the volume inside of the tubing. And this actually relies on P1V1 equals P2V2, or Boyle's law. So what we do is we start with the syringe at 0 volume. So what we have is we have at 1 atmosphere, or whatever the current atmospheric pressure is. So we're just going to say it's 1 atmosphere. So in the first condition, we have the pressure of the atmosphere, and then all we have is the volume of the tube, because we're starting with the syringe at 0 volume. So we have no gas in the syringe and only the gas that's in the tube. And then what we do is we pull the plunger back until we get the pressure to be 1/2 of the atmospheric pressure. So we start pulling back until the value goes down by 1/2. Then what we have, so on the right side, P2 and V2, we have 1/2 of the atmosphere, and then we have volume of the tube plus volume of the syringe. So whatever the volume is in the tube, we've added now some volume in the syringe, and that's going to be at 1/2 the pressure. So if you reorganize this expression a little bit, if we bring the 1/2 over to this side, if you divide both sides by 1/2, that's going to give you 2 on the left. So if you bring the 2 up, or if you divide both sides by 1/2, you get 2 on the left is going to equal V tube plus V syringe. So then if we want to get V tube by itself, we can subtract the V tube term from this side and subtract the V tube term from this side. So what we get is, at this condition where we're at 1/2 of the atmospheric pressure, we get that V tube is equal to V syringe. So by pulling it back to 1/2, we know that whatever the syringe value is going to be the volume that's in that tube. So we call this the correction factor. And for today, the correction factor is 8 milliliters. So when we pulled this back, we pulled it back and got 8 milliliters. So that tells us that there was 8 milliliters of gas inside the pressure vessel and inside this tubing. Okay, so the second part of this experiment is going to focus on using gas laws to accomplish a goal. And the goal that we're going to accomplish is to measure the molecular weight of a gas that we don't know what the molecular weight is. So how are we going to do that? what we're going to do is we're going to take an Erlenmeyer flask and we're going to seal it up with some aluminum foil that we're going to put a little hole in. And the unknown liquid that we don't know the molecular weight of it is going to go in here. And this liquid is an alcohol, so it has a relatively high vapor pressure, meaning that it evaporates pretty easily. So what we're going to do is we're then going to transfer this liquid into a boiling water flask. So there's going to be a beaker with boiling water, and we're going to heat it up, causing the liquid in the flask to evaporate. So we're going to basically make a gas inside of the flask. And we're going to heat this up until there's no more liquid left. And when there's no more liquid left, we know that this entire flask is filled up with the gas of the alcohol that's in there. And then from that, we're going to use the data that we collect to get the molecular weight. So what do we need to get a molecular weight? We need to get the mass, the gas constant, the temperature, the pressure, and the volume. So by heating it up, we've made our gas that's sitting inside of the flask, and it's now equilibrated with the pressure of the outside atmosphere. So the gas constant we have, that's 0.08 to 0.06 liters atmospheres per mole Kelvin. So that's a constant. So now we need the temperature. Well, the temperature of the gas is going to be the same as its surroundings, which is the boiling water. So on the day of the experiment, you would go in and put a temperature probe into the boiling water, and you'd get a temperature of 99.4 degrees Celsius. And we would write that down on our data sheet. So that's going to be written into your data sheet for you. Now, to get the pressure of the gas, we know that when this thing heats up, there's going to be a gas inside of here, and that's pushing out on this cap, this aluminum foil cap. And there's also going to be the pressure of the atmosphere pushing back. So when these two things equilibrate, the pressure that's inside the flask has to equal the pressure that's outside the flask. So we can use the atmospheric pressure as the pressure for the gas that's inside the flask. So in the lab today, we measure the pressure at 30.33 inches of mercury. So now you have to convert inches of mercury to atmospheres. And to give you a hint, to start, you might want to convert inches to millimeters of mercury, inches of mercury to millimeters of mercury. There are 2.54 centimeters per inch. So that might help you in this conversion. So you're going to get something close to about 1 atmosphere from this. And then that's going to give you your pressure that you need for the PV equals nRT. Now, we also need the volume of the gas. So the volume of the gas is pretty easy. It's the volume of the flask. So if the gas is inside of the flask, then the volume of the flask is going to be the volume that we need to measure for our equation. So the way that we get the volume of the flask is when the experiment is all done and everything is complete, you have all your data, you just fill this flask up with water and then pour that water into a big graduated cylinder, and then that will tell you what the volume was. So however many milliliters of water fill up the flask is the volume inside of the flask. So today, when you did that, when you filled up the flask with water and poured it out, you got 156 milliliters of water. So that gives you the volume of the gas in the flask. Now the mass. So the last thing we need is the mass of the gas. So at the very end of the experiment, we take this out. Once we have our gas that's in there that's filled up the volume, we take this out and allow it to cool. When the gas cools back down, it condenses and forms a liquid at the bottom of the flask. So what we can do is we can take the mass of the flask plus the condensed vapor, So we measure that after the experiment is over, and we get 95.8358 grams. And then we subtract from that the mass of the flask that we started with, which is 95.5791. So the difference between the flask and vapor and the mass of the flask is going to be that mass of the vapor. So you can use these two numbers to subtract to get the mass of the vapor. And then you have all three things five things you need in order to calculate the molecular weight. So the last thing I'd like to do is to give a little walkthrough of the data sheet so that you know what to do. So at the beginning of this data, these custom data sheets are uploaded to Blackboard along with all the rest of the other stuff for the experiment. So you can print these out, these two data sheets as is, complete them, and send them as part of the file to your instructor. So for this one, you have to send a couple of different things. You got to send these data sheets, and then you also have to send the graphs. So we'll talk about the graphs in just a second. So this is the calibration data. You could see that we started with atmospheric pressure, and then we had a 0 syringe reading. We pulled it back to half the pressure, and then we got a reading of 8 mils on the syringe. So this tells us that our correction factor is 8 mils. So for the volume of the gas in cc's, you're going to take your syringe reading and add the correction factor. So for example, this would be 30.0 mils. We add 8 mils, which is an absolute value. Treat this as an absolute value. So 30.0 mils plus 8 mils would be 38.0 mils. So you add them together. And then that's how you're going to get your corrected volume. And then these are the pressures as we measured them from the gauge. So then you can plot pressure versus volume, and then you can calculate 1 over volume and plot pressure versus 1 over volume. So on this page, we have the Amonton's law data. What we basically did was we took that metal sphere, we put it in different temperatures. So we started at ambient pressure and ambient temperature. We cooled it down to 3.5 degrees Celsius. We saw a slight decrease in the pressure. We raised it to 100 degrees Celsius. We saw a slight increase in the pressure. So this data is what you're going to use to make the Amonton's law plot. And remember, you have to extend that linear regression using a ruler all the way down to the x-intercept so that you can get the value of your x-intercept. So this should be close to 273.15. It might not be exact, and it shouldn't be exact because the data is not perfect. But you know, it should be close. So whatever you get for your x-intercept, you're going to want to put that here. And then this is the data for the molar mass of the unknown. So this was the starting mass of the flask. This was the temperature of the boiling water. This was the barometric pressure, and then this is the mass of the flask with and all the other stuff with the vapor, the condensed vapor inside of it. So using these two values, you can get your mass of condensed vapor. Now you'll notice in the slides, I forgot to put a decimal point on the volume of the flask. So because with the graduated cylinders, we can read off 1 extra decimal point beyond the marks, this data is correct, and you should use this in terms of sig figs when calculating the molar mass of the unknown. So just to show you with the graph paper, in your lab book, there are 2 sheets of graph paper that go along with this experiment. So here's what we're recommending that you do. On 1 sheet of graph paper in the book, you can create your pressure versus volume and your pressure versus 1 over volume graph. And you can choose how you want to do it. You can do them as portrait, as I show here, or you can have it graphed like the long way, however you want, whatever is going to make it work the best. But basically split 1 page in half for those 2. And then on a whole piece of paper, plot the pressure versus temperature of Amonton's law data. The reason why you want this is so that you have a nice long axis to plot all of your data for the temperature, because it goes over a really wide range of data, so that you can get your x-intercept. So that's everything you need to know for this lab. If you have any questions, you can ask your instructors, and I hope this is a good enough introduction to get you guys up and running.